Alright, semi-log plots. This entire chapter has been about exponential and logarithmic functions, the fact that they are inverses of each other, how to handle inverses from graphs, like ordered pairs, domains, ranges, equations, like that. You should, at this time, be able to look at the equation and determine whether it's logarithmic or exponential. You should be able to sketch that graph to determine its concavity, increasing, decreasing, all of that stuff you're going to see on the test on Thursday, including in behavior. So today is going to seem kind of disconnected to all of that, but it is relevant to logs and exponentials. And this is really one of the main takeaways that you're supposed to learn in this class. When you're dealing with a semi-log plot, and that just means that the y-axis is logarithmically scaled. And if you look right here, that's logarithmically scaled. 10 to the 0, 10 to the first, second, third, fourth power. Okay? When that happens, an exponential function will appear linear. That's a huge concept. That will be a very easy multiple choice question. So here's what that means. Here we've got some data that when it's plotted with just a normally scaled y-axis, we can see that that's an exponential growth. When I take those same exact ordered pairs and I change the scale of the y-axis to be logarithmically scaled, now it appears to be mostly linear. It's not a perfectly straight line, but you would be able to spot that as, okay, it's mostly linear. So if you had a test question on Thursday of a semi-log plot, and you guys asked a great question last time. This is also a semi-log plot at the bottom of your page. The one at the top is just missing the grid lines because it would have been too busy of a picture, okay? But this is a semi-log plot, and if you see that the dots are mostly in a straight line, then you're going to pick the answer choice that says this is exponential data, period. Okay. So all of that beneath there just says, look, the graph on the left shows the population using a normal scale on the vertical axis. The graph on the right is a semi-log plot. The vertical axis has been logarithmically scaled. And the data appears linear. Example 1. Use features of the semi-log plot above to justify why an exponential model is appropriate. You literally can just write, because the data appears mostly linear, and let's go ahead and expand on it just a tad. Mostly linear on a semi-log plot. The data is best modeled by an exponential function. Because the data appears mostly linear on a semi-log plot, the data is best modeled by an exponential function. Let's look at example 2. Alright. After this teacher tells a joke, begins to spread around the school. And the number of people that have heard the joke after 2 minutes is graphed on the semi-log plot. Where the vertical axis has been logarithmically scaled. We've actually done it. Semi-log plot is. Which of the following functions could be a model for you? So, here's what, as a student, here's what your thought process should be. I notice that it's mostly linear on a semi-log plot. So I need to pick the answer choice that's an exponential graph. There are 2 answer choices that right away I can mark out. Which 2 answer choices are not exponential functions? A is linear, and C is logarithmic. That leaves B and D. And they look kind of similar here. Yes. I don't think so. And that's not in our little Bible we teach out of. That's not in there, so I don't think so. So these look similar. We've got 2 plus 2 to the t power. We've got 2 times 2 to the t power. Look at this ordered pair right here. The ordered pair for that point right there is 0, 2. That tells you that the starting value is 2. That's our A value. And if you'll remember, when we write exponential graphs, it's like A times B to the power of x. So the starting value is A. A is 2. And then you could pick another ordered pair, and you could just kind of plug in and see. But that means if I plug in 0 for x, I should get an output of 2. Let's try that right here. If I plug in 0 for t, what's 2 to the 0 power? 1. Plus 2? That's 3. That's not what I'm supposed to get. Plug it in down here. What's 2 to the 0 power? 1 times 2? 2. That's the number. I mean, I can't say never, but to me, I would have just picked this one because this is not really, this is an exponential graph that's been moved up to, it's been transformed. And we don't typically see those. I guess it could be that if you plugged into this one a couple of these ordered pairs and it matched that, then that would be an answer. So I can't tell you that it's always going to look like this, if that's what you're asking. Don't make any assumptions going into this. When you logarithmically scale a vertical axis, you're not actually changing the value of the data. You're not changing the y values of the data. Those ordered pairs from the original data remain the same ordered pairs. It's just going to look differently in the graph because of the way that it's scaled. I think that is kind of an obvious thing. Now, let's look at how easy this question is. The table above gives selected values for a function. Which of the following graphs could represent this data on a semi-log plot where the vertical axis is logarithmically scaled? Well, just look at your answer choices. Which one looks like a semi-log plot? D, okay, but I can justify that by saying, look, on A, that vertical axis is not logarithmically scaled. On B, technically it is logarithmically scaled, so we'll come back to that. C, that is not logarithmically scaled, and D is, okay? So let's just kind of figure out why B would not be the answer. Well, look at this first ordered pair. It's 140. And this would be 1 like 3/4. 1 3/4. Whereas here, I can find the ordered pair 140. We've practiced plotting on these before, so remember that every line above the 10, between the 10 and 100, is counting by tens. So 10, 20, 30, 40, 140. It's got to be D. Semi-log plots are always going to look the same. They're always going to have like this kind of gap, big gap that gets smaller, and then a big gap that gets smaller, and a big gap that gets smaller. That's easy. Let's practice plotting points on here, just to make sure we remember that. We've seen this in notes before. Plot the following points. Point A needs to go at 0, 200. 200 is going to be up here in the hundreds, and it's going to be on the first line above 100. And you've got tons of these on your homework, just to practice and get comfortable with. B, 1, 25. So I'm going to go 10, 25. There's B. C is 2, 7. 2. 1, 2, 3, 4, 5, 6, 7. There's C. 3.2, 800. Well, don't freak out at the 3.2 because this is 0.2, 0.4, 0.6, 0.8. So 3.2, and then 800 is way up here in the hundreds. Right up there. And then E is 4.6, so 0.2, 0.4, 0.6. 1.5 is going to be right here between the 1 and the 2 in that space. Pretty easy. We're almost done with the notes. So here's where things get a little bit tricky. It's going to be intimidating in the beginning, and I'm hoping that it'll all come together in a way that you're like, oh, that really wasn't that bad. Hopefully, we'll have to see. One thing that you're supposed to know is when you see on a semi-log plot that the data is linear, one of the things that they might test you on is being able to write the equation of that line. Like, think y equals mx plus b, okay? Y equals mx plus b. What should I just type? What is in the place of m for mx plus b? Log base n of b. So guess what? The slope of that line in that semi-log plot is log base n of b. Y equals mx plus b. Look what's in the spot of b. That's your y-intercept. The y-intercept is log base n of a. Where are they getting this a and this b from? And it's right here. If you know your exponential model, you know the starting value, which is a, you know the rate at which things are growing, which is b, then you're just going to be able to rewrite it in this form of y equals mx plus b by taking log base whatever of b times x plus log base whatever of a. And I promise I'm going to show you that right now in example 5. The semi-log plot above corresponds to the data table from example 3. Using ordered pairs from the semi-log plot, determine the values for a and b, and write the equation of the exponential model. Now he had it backwards, and I like to go in this order when I work these. Okay, he had you starting out. The guy that made this had you starting out with the linear one, and then writing the exponential, and that just seemed clunky and weird, and just didn't make a lot of sense. I think it's going to be easier for you to look at this data, figure out a and b, and then write the exponential model with a and b in. So let's look at some ordered pairs. We've got, I'm going to make a little table here. And really, you could probably just do this with 2 ordered pairs. Like the first one I see, what ordered pair is that? 1 what? 40. And the second one here is 2 what? 60. Now, I'm going to work a homework problem with you that's like this because I don't feel like one example is enough. But let me make something very clear. The homework example I'm going to do with you is slightly different. I want you to notice right now that the x values go up by 1. That's the only reason why I'm allowed to do what I'm about to do. Because the x values are increasing by 1. If you can figure out what we're multiplying by to get from 40 to 60, then that's going to be our value for b. It's the rate of growth. How do you figure out what I'm multiplying by to get from 40 to 60? It's a fast way. Divide. Yeah, 60 divided by 40. 6/4 without a calculator. That's 3 halves. So we're multiplying by 3 halves to get from 40 to 60. Once again, the only reason I'm able to say, oh, that's b, is because my x values are increasing by 1. In the homework example, our x values aren't increasing by 1, so it won't be this simple. Now, here's what I know. Go down to part A. B is 3 halves. So now I can kind of start my process. Y equals A times B to the x power. I just need to figure out A. Well, what you can do is you can use any ordered pair you want and plug in that x value right here and that y value right here, and that'll allow you to solve for A. What point would you all like to plug in? Let's choose one of these. 140 sounds fantastic. So I'm going to plug in 40 for y and 1 for x. That makes this pretty easy. 3 halves to the first power is just 3 halves. So as I'm moving right along here, multiplying by 3 halves, how can I get rid of that? You could divide by 3 halves, that's kind of funky. What did your 8th or 9th grade teacher say? Multiply by the reciprocal, multiply both sides by 2/3. 40 times 2 is 80 thirds. Here's A. That wasn't terrible. So I'm ready to write the answer. The exponential model for this data is y equals 80 thirds times 3 halves to the x power. Yes. Yes, so you're saying go here and divide by 2/3? Yes, and that's what I'm going to show you in the homework too, so you can find your. When you did that, did you get 80 thirds? Perfect. So Addison's just saying if you wanted to work backwards in the table to find your 0, whatever, because that's your starting value, then you could just divide backwards and you're going to get 80 thirds in that spot. That's great. It's fantastic. And if you're like, huh? I'll show you in homework. So here is where we're going to use this exponential model, and we're going to be able to write it in a linear way. Okay. I'm just following here. It's like reading code. Y equals mx plus b. M is, if I'm looking back up in that box, the slope is log base whatever of b. Now I say log base whatever. In this context, it's going to be log base 10 because this is all in log base 10. It's a semi-log plot. So the slope is log base 10 of b, and we figured out b was 3 halves. So that's m x plus our y-intercept. Our y-intercept is log base 10 of a, and a is 80 thirds. There's not any math to do, it's just kind of plugging things in where they go. And it looks crazy. And it's not going to make any sense to you right now that that could be a slope and that could be a y-intercept. But it is what it is. That's how you take these data points and come up with the equation for the line of those. Yes? I would not, again, I wouldn't make any assumptions. I would not guarantee that they would have this embedded in the problem for you.
Is it always log base 10?
And when you're working with semi-logs, yes, absolutely. Now, that's it on the note.